Welcome to our linear programming learning video for operations management presented by Group-56. This is Steve. After he graduated from the University of St. Gallen, Steve founded his own watch company called Polix Watches. He started with two base models, the Superman and the Lobster Perpetual. In a meeting with his production team and the suppliers, the following quantities for production were given. A maximum of 12 Supermans and 24 Lobsters for 432 labor hours. A maximum of 15 Supermans and 16 Lobsters may not exceed 900 units of steel, and only 30 clockworks for the combination of 1 Superman and 1 Lobster are available. Steve now wants to optimize his total profit, but he doesn't really know how to apply the information that he just received. So, he contacts his friend Leopold, who visited the Introduction to Operations Management course at HSG. Leopold introduces Steve to the concept of linear programming to maximize Polix's profit for this period. Linear programming is an extremely valuable mathematical modeling technique used by many companies for optimization under the given constraints. In today's highly competitive market, the application of linear programming has become a vital part of company survival. The goal is to find the best possible solution for several input factors with given constraints by finding the best product mix to either minimize the costs or maximize the profit. To apply linear programming, we need to outline certain characteristics that all models must have. First of all, the objective function, which is the target which we want to optimize. Then, non-negativity. We cannot produce a negative output. Thirdly, linearity in the form of an equation or inequality. And lastly, the constraints. For example, maximum input of raw materials. Leopold has used linear programming and created the following graphs to find the optimal solution based on the constraints from the production team. First, we need to plot the constraints provided by Polix production team on the graph represented by the yellow, green and red lines. The area below their points of intersection show the feasible product mixes that satisfy our constraints and is shown by the blue shaded area. Now, to find the optimal solution that maximizes our profit within the target region, we use the profit function z equals 450s plus 270l, which we obtain by using our profit unit model. In our case, we used a z-value of 2700 and plotted this on the graph. To find the optimal solution, we move the z 2700 line in a parallel manner, as shown in step 1 and 2, towards the optimal corner points on the right. The optimal solution is equal to the coordinates where the optimal order points and z-line intersect on the farthest right. To find the coordinates of that point, we set a simultaneous equation between the constraints for clockworks and labor hours. This equation leads to a solution of 24 Supermans and 6 Lobsters as shown in the image on the spreadsheet. Plugging these values back into the profit function, this yields a total profit of 12.42 million. Although graphical linear programming worked well in Polix's case, Leopold informed Steve that this method also has major limitations, namely the fact that it works only for 2 decision variables. Furthermore, graphical linear programming can also have certain special features that limit its applicability as a method. These are as follows. First, we have the case of infeasibility, where there is no solution that satisfies all constraints. This can occur when the problem has been formulated with conflicting constraints, meaning no feasible region can be obtained. In the example case, the constraints for labor hours and clockwork creates a feasible region. However, the constraint for the Superman model is conflicting and no solution exists. Next, we have the case where there are no corner points on the bounded side, meaning the value can be infinitely large without violating any constraints, and the feasible region is unbounded. This usually occurs when the problem has been wrongly formulated or the constraints are simply wrong. In our example, the constraints do not limit production, meaning there is no limit on the profit that can be made. This unbounded solution is represented by the blue shaded region. A redundant constraint is a constraint that has no impact on the feasible region. For example, in our instance, the green line that represents the constraint for steel has no impact on the region represented by the blue area. In other words, if we would remove it, the solution would not be affected. Linear programming problems can have alternative optimal solutions. This occurs when the constraint and the profit line have the same rate of change, in other words, the same slope. For instance, here the profit line and the red line representing the constraint for clockworks overlap and thus create multiple solutions, represented by the feasible solution range. Following the success of the Superman and the Lobster Perpetual in 2021, Steve decides to introduce 2 new models, the Nightona and Earth Dweller. Furthermore, he has purchased a new production machine in order to reduce the direct labor hours. He also plans to use some gold in his watches to increase their rarity and be able to sell the watches for a higher price. The Polex's marketing sector recommends producing at least 1,000 units of the Lobster Perpetual, since they think this model will appeal to customers in East Asia, a market sector they would like to penetrate. They also say that Polex should produce more units of the Nightona rather than the Superman. Based on this new information, Leopold informs Steve that graphical linear programming will no longer be possible due to the number of new products and constraints. Instead, he creates a new Excel spreadsheet that performs linear programming using the Solver tool. Here, we're going through Leopold's spreadsheet of the linear programming optimization problem of Polex watches for 2022, the goal of which is to find the optimal production solution for the given four models. Linear programming can be used for lots of different settings, and in this case, we're using it to find the profit-maximizing product mix. We are limited to the available resources on the right-hand side, which must be greater than or equal to the left-hand side, which are the quantities we used. To find our profit, we must find the quantity per product that needs to be produced according to our constraints. At the top of the screen, we have our decision variables, which are the number of the units. Let's put in some random numbers. Let's say 10 units for each model. Now we apply the sum product formula, which multiplies the numbers of units by its respective costs. Here we choose the decision variable C4 to F4, hit the F4 key to fix them, and select the representative row. In this case, labor hours, which are C8 to F8. Now we can drag down the formula as we fix the decision variables previously. For the total profit, we multiply the number of units with the respective profit by using the sum product formula. For our special constraints, we want to focus on the Lobster Perpetual model, therefore we put in a 1 in cell F15 so that the sum product formula only takes that into consideration. We do the same for the second special constraint and put a 1 in the cell F16 for the Nightona. We also put equals D4 on the right-hand side of the 16th row to ensure we fulfill this constraint. Looking at our model, the current configuration of products yields a profit of 21.56 million, but as you can see, there's a vast discrepancy between the left-hand side and the right-hand side, meaning we're not using our factors of production to fullest capacity. Now, let's assume we produce 30,000 units of each model. Our obtained profit now is equal to 64.69 million. This solution would generate significantly more profit. However, looking at the left-hand side, we can now see that we used more resources than we actually have available, and thus it is not a feasible solution. Now we could try to find the optimal product mix by changing the numbers manually and finding a solution that works. However, this is extremely inefficient and may not yield maximum profit. Thus, as a solution, we apply the solver. We must go to the Data tab and then go to Solver. Now we got our objective, which is the total profit in cell C18, and by default it will try to maximize this cell. Now the variable cells are our decision variables, the number of units we want to produce for each model. So we highlight cells C4 to F4, and next is the subject to our constraints. Our constraints are that the left-hand side values must be less than or equal to the right-hand side values. Thus, we click Add, select the two cell references, check that the sign in the middle says less than or equal to, and hit the OK button. Now we must add the special constraints to the solver, as we showed previously in our Excel. Our final constraint is that the variables must be non-negative, since we cannot have negative outputs, and thus we check the box Make Unconstrained Variables Non-Negative. The solving method we want to choose is the simplex LP method. Now we click Solve. If we set it up correctly, the solver says Solver has found a solution. Additionally, we click on the respective reports which we want to use. Now our final solution gives us a profit of 46.6 million. The profit maximizing product mix is 23,000 Nightona models, 15,000 Superman models, 39,000 Earth Dweller models, and 1,000 models of the Lobster Perpetual. As we can see, all of our constraints are met, and the use of the factors of production is optimized. However, this will be discussed further in the reports to follow. The sensitivity report deals with the inputs, our decision variables, and our constraints. The objective coefficient shows you the profit per unit. The allowable increase and decrease show much higher or lower, respectively, the profit for each unit could be before we obtain a different product mix. For example, the price of the Earth Dweller model could be $24 higher or $65 lower before it would change the quantity to be produced. The outcome of 1e plus 30 is Excel's way of saying that the change could be infinitely large.